Hi, so in this section we're going to go over the method of cylindrical shells to calculate volumes of revolutions. So first consider the problem of finding the volume of the solid rotating the function y equals to x squared minus x cubed around the y-axis, and that is given around this graph. Notice that we're taking this whole area and then we're rotating this around the y-axis. The problem with this is that it's not as easy to do with the washer method. Why? Because the washer method requires that we're able to find the internal radius and the external radius of the given cross-sectional area. But the problem is that we cannot very easily identify what is this point in terms of that precise variable, which will be y. Here we will need to put our function, which is now in terms of x. We will need to transform this in terms of y, because remember that if we're talking about rotating about the y-axis, then the radius is the distance from here to here, and this is a value of y. So we need to say x is equals 0 here, and then x is equals this much here, and thus x is equals this much here to be able to calculate distance between x equals 0 and x equals whatever this point is, and x equals whatever this point is. The problem is the function cannot be solved easily in terms of x. Y equals 2x squared minus x cubed is not a function that we can say, oh, okay, so let me move around the x and I'm gonna find out what is it in terms of y. It's not as easy. So what we do instead is we're gonna use the method of cylindrical shells. So what is that about? Well, we're gonna do pretty much the same notion as before, but remember with this or washers, we were taking perpendicular pieces to the axis. We were taking perpendicular cross sections to the rotating axis. Now instead, what we're gonna do is we're gonna take parallel cross sections to the rotating axis. Now, in this example here, we have a curve between the interval a and b, the points a and b. And so because we're rotating around the y-axis, this is going to produce this type of volume. Now, of course, the cross-section, if I take a cross-section that is parallel to the rotation axis, then when I turn this around, this is going to produce a bunch of different cylinders. And if we divide the interval a, b into n sub-intervals of equal width delta x, and let x be the midpoint of the sub-interval, we're going to end up with a situation like this. So we're trying to approximate the whole volume, and then we start first with a single cylindrical shell. Notice that that cylindrical shell is given by the length of a circle around, then the thickness of that particular circle, and of course the height, which is given by the function f of x, which is what's going to give me the height of the cylinder. So what ends up happening here is that we have a bunch of cylinders that are approximating what is the volume of the solid. And then what we do is the same thing that we did before, and is we're going to reduce the thickness of the cylinder shell, and so we're going to have a bunch of much more, so we can approximate without error or with much less error the volume of the solid. Now the volume of one of these pieces is going to be given by 2 pi xi, which is the length of the circle around the midpoint xi, by the thickness delta x. So this is what produces this ring down here. So that produces the area of that ring. But then later it's going to become a volume because we multiply by the height. So we remember the volumes are area by height. So we have here 2 pi xi, which is the length of the cylinder, by delta x the thickness, so it gives me an area, and then by f of xi, which is going to give me the height. So now what we do again is we take the limit when n goes to infinity of that, we reduce the thickness to be almost nothing, and so that's going to give me the integral here. And so I get a new integral for this method. The method of cylindrical shells can be represented by the integral from a to v of 2 pi x f of x. Now, this x, of course, is because we're considering the distance to 0, to the x equals 0, or the y-axis. If we move the axis, then this can be x minus something, x plus something. This can change in here, okay? And you'll see more of that on the practice videos. But now, let's go and check what this means. So the volume of the solid before is given by this integral in the interval a to v. So just recall that when we're taking these cylindrical shells, each of these pieces means something. The circumference is given by the 2 pi x, and then x is the difference from the rotation axis to the edge of the cylinder shell. Delta x means the thickness, and f of x is meaning the height. Okay? And so we're having this situation where we're pretty much analyzing what is the area of a particular sheet, which measure 2 pi x by f of x, and it has a thickness then delta x that transform the whole thing in a volume. Now let's see an example of how that's going to help us to solve the previous problem. So we have the function y equals to x squared minus x cubed, and it was turning around the y-axis. Okay. Now here, this is the sketch of that situation. So we're going to take one piece, one cross-sectional piece, which is going to give us just the f of x, to x squared minus x cubed. So I don't have to do much with this. And I have that the distance from the axis to the edge is going to be x as well. So this is going to work out with the previous formula that we have. And by the shell method, this is only going to be the integral from 0 to 2. And notice that it's from 0 to 2 because it starts here and it finishes here at 2. And the circumference, 2 pi x, the height, which is a function, to x squared minus x cubed, and the thickness, delta x. So when I multiply this and I pull out a constant, this becomes 2 pi, integral from 0 to 2 of 2x cubed minus x to the 4 dx. I integrate the powers, and then I have to integrate the powers. I plug on the numbers, and that's going to give me a 16 over 5 and times pi. You can verify this. The shell method is going to give you the same answers as the slicing method if necessary. And so that poses the question, what is better? Do I use disc or washers or cylindrical shells? When am I going to use this? And can I use both for the same kind of problem? And the answer is yes. Sometimes you can use both, but there are definitely going to be some scenarios where it's much more easier to use one of them than the others. And that's what you need to learn to identify when is that going to happen. A lot of the things is check the situation and see how the solid of revolution is. Do I get something more easy to work with if I'm working with perpendicular to the axis of revolution, with a perpendicular cross section to the axis of revolution, or do I have an easier time by doing a parallel cross section to the axis of revolution? Okay, that also means it's going to be easier to work the integral in x, or it's going to be easier to work the integral in y. Okay, all those considerations is what gives me the choice of variable, of what's going to be easier, and that's going to also mean the choice of method. Okay, so let's see an example of one of those where you can actually do it by both methods, okay? And then later we'll have the opportunity to see in the practice videos where do you use better one or the other. Now, for the following example, we have the bounded figure in the first quadrant between the curves x squared and 2x. A solid is going to be formed on that region by rotating about the line x equals -1. So notice here we're changing the axis of revolution. It's not going to be the y-axis anymore. It's going to be x -1. We're going to find the volume of the solid by the two methods. So this is the situation. We have the function y equals 2x, which is this line, and the function y equals x squared. This is producing this solid. And we're rotating around the x equals -1. Now, to find the volume using x as the variable integration, then we gotta use a parallel to the axis of rotation. So we're gonna use cylindrical shells. You can see here that when you use the cross section, you get a cylindrical shell. That's something that you're also gonna do when you're doing your own exercises, and is make sure what is the axis of rotation, and are you going parallel to the axis of rotation or perpendicular? If depending on that case, then you're using better cylindrical shells or you're using washers. In this case, notice that because it's parallel to the axis of revolution, then we're gonna start with cylindrical shells, and also we're gonna keep the variable in terms of x. Why in terms of x? Because this function can be represented as y equals 2x. This can be represented as y equals x squared. Okay. Now, I can establish the difference between these two in here. So how that's going to be? Notice the rotating region about the line x equals -1 produces a cylindrical shell, so the volume is going to be 2 pi x plus 1, because remember this part here is the distance that we have from here, from this location to here. So this is a certain point x that I don't know what it is, x minus -1, so x plus 1. So that's where I get this part. Remember before on the graph we always had this distance, we were measuring this distance. It was x here because we were measuring the distance to a point x from 0, and so that's why it's 2 pi x. But now in this case is x plus 1 because it's from certain x to -1. Now f of x here, the f of x is given by the difference between two functions. Here it's not going to be one function anymore, but we have the area enclosed between two functions, and so we make the difference between the variable, the function on the top minus the function on the bottom, like in any of the areas. And so we have 2x minus x squared, and so that's what we have over here. Once that we have this set up, then everything is complete. The only thing that we need to do is integrate. We multiply this out. We get that this is 2 pi, the integral 0 to 2, x squared plus 2x minus x cubed. Integrating that by power rules and plugging is going to give us that this is 16 pi over 3. Now let's take a look at this from the other method. Okay. Notice that if we're going to use we're going to find the volume using y as the variable integration. First thing, we're going to have to change everything to in terms of y. Here we're going to have x equals 1/2 of y. Before it was y equals 2x, so x becomes 1/2 of y. And we have y equals x squared, so that function transforms into x equals the square root of y. Now notice that now we're checking the radius, the inner radius and the outer radius. So we have here a washer situation. And clearly the inner radius is given by the 1/2 of y, and the outer radius is given by x equals the square root of y. Okay, the thickness of this is going to be delta y. And so when we have this, we can use the washer method in here. Notice that the washer is pi r squared for both of those. So we have from 0 to 4, because now we're talking about in terms of y. So when x is equals 0, is 0, but when x is equals 2, we have that y is equals 4. So now my variable integration changes to from 0 to 4 of pi r squared, pi outer radius squared minus pi inner radius squared. And let's check what the inner radius is. So the inner radius is the distance from this point that is given by 1/2 of y to minus 1. So the distance from here to here will be 1/2 of y minus minus 1. So the inner radius will become 1/2 of y plus 1. The outer radius, on the other hand, will be square root of y minus minus 1. So will become the square root of y plus 1. Okay? And so that's why the volume is established here as the integral from 0 to 4 pi the square root of y plus 1 square minus pi 1/2 of y plus 1, everything is square. And so once that we compute this, we can open the binomials here and simplify. Then we're going to get that this is the integral from 0 to 4, 2 square root of y minus 1 over 4 y squared. And then integrating this, we're going to have this is 16 pi over 3 again. Notice that the volume coincides. So on both scenarios, if I was doing cylindrical shells or if I was doing washer shape, they're going to coincide both. Okay, so this is the end of the introduction to the method of washers and cylindrical shells. Make sure to check the practice videos so you can have more examples of this.